All right, we're going to go through each homework question one by one. We'll do a little review and look at a handful of the problems from the review sheet. So in 35, because we're raised to the n, root test would be a good idea. Limit as n goes to infinity of the nth root of our expression. We eventually get something with same degree, so ratio leading coefficients is a half. Because that's less than 1, we would say converges by the root test. Similar idea in 36, but this time ratio of leading coefficients is 2, which is greater than 1, so we would say diverges by the root test. In 37, when we take our nth root, we get 1 over natural log of n. Denominator gets huge, so that goes to 0, less than 1, so converges by root test. When we take the nth root in 38, we get something that's cubed. But as n goes to infinity, that thing in the parentheses will approach 3 halves. 3 halves cubed is 27/8, which is bigger than 1, so we would say it diverges by the root test. Next one, we're raised to the n, so we do root test. As n goes to infinity, that's really n to the 1 over n. Well, that's going to give us an infinity to the 0, which is indeterminate, so we got to take that off to the side. So I pulled that limit down to the next row. Our technique with an indeterminate exponential part, we do e to the natural log of our thing that we have. Then we set the e aside, and we just do the limit of the natural log of n to the 1 over n in this case. Log laws allows the 1 over n to swing out front. 1 over n times natural log of n is the same as natural log of n over n. As n goes to infinity, those will each be infinity, so we can do L'Hopital's. Derivative of bottom is just 1. Derivative of top is 1 over n, so we end up getting 1 over n when it neatens. As n goes to infinity, we get 0 for that, but remember is really e raised to that. E raised to the 0 is 1. If we put that back into our expression, that's now 2 times 1 plus 1, which is 3. 3 is greater than 1, so we diverge by the root test. That was probably one of the most complicated ones on this homework assignment. For 40, when we do our nth root, we end up with e to the negative 1. That's the same as saying 1 over e, which is less than 1, so converge by the root test. In 41, when we do the nth root, we get 1 over natural log of n. Bottom's going to get big, so that's going to go to 0. Less than 1, so converge by root test. For 43, we're using any that we think would be best. Notice we've got the minus 1 there, so we're alternating signs. If we look at a few terms, the numerator staying constant, denominator is getting big, so each successive term is less than the one before it. Our individual terms will approach 0, so we can say converging by the alternating series test. In 44, we can pull out a 5, and then we're left with 1 over n, so that's harmonic, so it diverges. Or you could say it diverges because it's a p series with p greater than 0, but less than or equal to 1. In 45, you can pull the 3 out front, and then that's a p series with p greater than 1, so that converges. 46, we're raised to the n. So we have two options. We could do root test. We end up getting pi over 4 left, which is less than 1. So you can say converges by root test. Or that's actually also geometric. 3.14 over 4, the absolute value of that is less than 1. So you could also have said converges because it's a geometric series with absolute value of r less than 1. (47) as n goes to infinity, the individual terms are approaching 2, so that means we must diverge by the nth term test. In 48, we want to force those to have the same degree, so let's compare to 1 over n, which is something we know diverges because it's harmonic. When you divide those two series, we end up with n squared over 2n squared plus 1. That will approach 1/2. As long as that approaches a positive finite number, then we know our series will do the same thing as our nice series. We already said our nice series diverged, so we would say our series diverges by the limit comparison test. '49, we've got all these different powers to the n. So ratio test might be a good idea here. Do next term divided by current term. When you do keep, change, flip, you get 1 extra 2 in the denominator, 1 extra 3 in the numerator. 3/2 is greater than 1, so that diverges by the ratio test. In 50, pull out the 10/3. You're left with 1 over n to the 3/2. So that's p series with p greater than 1, so we're converging. In 51, this one is a little bit tricky. The n parts have the same degree, so we want to force the numerator to also have a 2 to the n. So we're going to compare this to 1 over 2 to the n. 1 over 2 to the n can be thought of as 1/2 raised to the n, so that would converge since geometric absolute value of r is less than 1. If we divide our two expressions, that 2 to the n swings up on top. Well, then the 2 to the n's would divide out, and our remaining part, as n goes to infinity, would approach 10, which is greater than 0. As long as it approaches a positive finite number, our series will do the same thing as the nice series. We already stated that our nice series converged, so our series we wanted to examine must converge by the limit comparison test. So if we write out a few terms, it appears like they're getting bigger. Because, for example, 32 over 99 is less than a third, but 64 over 107 is more than a third. So it looks like they're getting bigger. So let's maybe investigate nth term. As n approaches infinity, you get infinity over infinity, so do L'Hopital's. Then you'll get infinity over infinity again, so do L'Hopital's. Only n's are left in the numerator, so that will go to infinity. Because the terms aren't going to 0, that diverges by the nth term test. '53 was the other pretty tricky one. So what we can do is recognize if you did the absolute value of our series, it'll always be less than or equal to 1 over 2 to the n. The reason being, cos stays between -1 and 1. So the biggest the numerator could be is 1, but most cases it'll be something smaller than a 1. We know 1/2 to the n converges because it's geometric. Absolute value of r is less than or equal to 1. Therefore, by direct comparison, we know the absolute value series is going to converge. Well, if the absolute value converges, then we know the original must be absolutely convergent. Therefore, our original series must converge. So that one was a little tricky. 54 is a little bit more straightforward. You're alternating. Each term is getting smaller than the one before it. Our terms are going to 0, so we converge by alternating series test. All right, so if we review a couple things first before we do some problems. This is in your packet under the day 10 review. So you want to make sure you're comfortable with the difference between a sequence and a series. So a sequence is a list of numbers. And a series is a sum of a sequence. You want to be comfortable with the difference between a sequence converging and a series converging. If a sequence converges, you approach some number. Could be anything, but the terms are getting closer and closer to some number. So maybe let me throw that in there. The terms approach some number. In a series, if a series is going to converge, the terms must approach 0. And the partial sums approach some number. So the individual terms need to go to 0 if the series is going to converge, and the series will approach some value. But if a sequence is going to converge, we're just saying the terms are getting closer and closer to some number. Doesn't have to be 0, just getting closer and closer to some number. There's only 2 series we can actually calculate the geometric or the infinite sum. One of them is geometric. And for finding that, we do a1 over 1 minus r to find our geometric sum. And the other is telescoping. And to find that sum, we do limit as n approaches infinity of the remaining terms. Remember with that, however many terms there are on the front end that didn't wipe out, the same amount of terms on the back end in terms of n should be there as well. And then just let n go to infinity, and whatever you get for that limit will be the actual sum of the series. For any other type of series, the best thing we can do is evaluate it is to find partial sums. So in other words, we can take a finite number of terms, add them together, and that will get us reasonably close to the infinite sum. And there's 2 ways we can calculate our error, or in other words, how close we are to that infinite sum. The first way is with an alternating series. The absolute value of our remainder is less than or equal to our next term. And when we say our next term, we mean our next term like without the negative, because it's alternating. So if you have an alternating series and you want to deal with the remainder, you should be putting n plus 1 in place of the n's. The other is with our integral remainder. Your remainder will always be less than the integral from n to infinity of f of x dx. So if you do the 10th partial sum and you want to know how close is that to the infinite sum, well, we can do the integral from 10 to infinity. Whatever number we get is an upper bound, okay, something we know is definitely greater than that difference between the infinite sum and the 10th partial sum. A reminder on the review sheet that 0 factorial by definition is 1. And we're going to do 6 problems from the review sheet that in years past have been ones that have been asked to go over. And then any remaining time in the period you can work on the review sheet. So we're going to start with question 3. So this one is asking for an expression for the nth term of the sequence. Notice this is not a series, it's a sequence. So we would just say an, and we got to look at our pattern. Well, you can think of these as being over 1. Your numerator goes -2, 4, -8, 16. So really just we're multiplying by -2 over and over again. Since our first term must be a1, we can have this be just to the n, so that when we sub in 1, we get a negative, 2, we get a positive, and so on. Now, you could have also done separately the negative and the 2's. You could have done -1 to the n times 2 to the n, and that would be perfectly fine as well. Now, for the denominator, we need to think about how are we getting 1, 1, 2, 6? Where are those coming from? Well, 6 is really 3 times 2 times 1. So that's 3 factorial. 2 is 2 times 1, so that's 2 factorial. This is 1 factorial, and here's where that 0 factorial being defined as 1 comes into play. So our bottoms are just a factorial. Notice the fourth term, though, has 3 factorial. The third term has 2 factorial. So our factorial is 1 less than our number of terms, so we would have n minus 1 all factorial. Our next one we're going to look at is 14. We want to know whether this converges or diverges. Well, when n goes to infinity, that plus 5 really isn't going to be doing much. So kind of like when we have the same degree in numerator and denominator, we can really think of it as it's just going to be the factorials in numerator and denominator. So therefore, when we do limit as n approaches infinity of this thing, when n is enormous, really just the factorials are going to matter. So they will be in the ratio of 2 to 3. So we can do a similar idea when we've got those factorials there of ratio leading coefficients as we can when we have same degree. Well, that's not equal to 0. So we can say that this series would diverge by the nth term test. We're going to go over to 15 next. We want to find one that diverges by the nth term test. So we need our individual terms to not go to 0. Well, in the first one, we've got same degree. So ratio of leading coefficients is 1 over 1. So this is going to approach 1 for the terms. We need it to approach 0, so that's our 1 right there. It's going to diverge by nth term test. But let's just talk about the other ones. For the second one, as n goes to infinity, we essentially have infinity over infinity. So you could do derivative of top and bottom. Derivative of the top, you would multiply the 11 down, you'd have n to the 10th. And on the bottom, you've had 5 to the n times natural log of 5. Well, you'd get infinity over infinity again, and you'd have a whole bunch of L'Hopitals. The denominator is always going to have a 5 to the n. The numerator, eventually, when you do enough L'Hopitals, you'll have a constant. So a constant over something with a 5 to the n, well, the bottom will get big, so that'll approach 0. In C, the factorials are going to grow bigger than that linear thing, so that'll approach 0. And in D, bottom will get big, top's 11, so the terms approach 0 there. We'll look at 19 next. So it should be added in there in 19. We want to select all that apply that would diverge. In A, we want to think a P series. P in that case is 5 halves, which is greater than 1, so that would converge. So we can rule out choice A. In B, pi is 3.14, E is 2.7. So we have a numerator that's bigger than a denominator. So your absolute value of R in that geometric would be greater than 1, so that's going to be a diverge. So B definitely works, meaning we can cross out E. In C, as n approaches infinity for your terms, ratio of leading coefficients is a half. So those terms are approaching a half and not 0, so that's going to diverge by nth term test. And then in D, that's geometric, but this time the absolute value of R is less than 1. So we can converge for that one. So B and C would be our two that would diverge in this case. We're going to look at 24 next. So S represents the infinite sum there. And we want to use the fourth partial sum to approximate the infinite sum. Well, so what we're going to do first is let's actually just find that fourth partial sum. So we would do n equals 1 to 4 of 8 over n squared, and we would get 205 over 18 for that. Well, we are guaranteed that the fourth partial sum is less than the infinite sum. So far what we know is 205 over 18 is definitely less than our infinite sum. Because we would be adding, the infinite sum is definitely going to add on more terms than that. Well, what we've got to figure out is what's our upper bound? What should be on that high end that we know the infinite sum doesn't go beyond? Well, this is not alternating, so we can't use our alternating error. So we've got to do our integral error. The integral error is going to tell us an upper bound of how much extra you would have to add to get to the infinite sum. And we're guaranteed that extra is really too much. So if we can do our integral error, like let's say it was 3/18 hypothetically. Then on our right side of that inequality, we would put 208/18 because we would know that 3/18 is bigger than the actual gap between the fourth partial sum and the infinite sum. So what we're going to do here is we're going to do our integral from 4 to infinity of 8 over x squared dx. That would mean we're doing limit as b approaches infinity from 4 to b. I'm going to write this as 8x to the negative 2 dx. So new exponent's negative 1, divide out front by negative 1, and we're going to get negative 8x to the negative 1, or in other words, negative 8 over x. And we're going from 4 to b. Well, this is going to be limit as b approaches infinity. We'll have negative 8 over b minus a negative 2. Well, this will become plus. As b goes to infinity, that first fraction goes to 0, so this is 2. So what this tells us is the fourth partial sum is definitely within 2 of the infinite sum. Or in other words, if we added 2 to the fourth partial sum, we're guaranteed it's greater than the infinite sum. So what we're going to do is we're going to add 2, or in other words, 36/18 to the fourth partial sum, and that would give us 241/18. We're guaranteed that it's higher than our infinite sum because we knew that 2 was definitely bigger than the gap between the fourth partial sum and the infinite sum. So hopefully that's a choice. Looks like that is choice D. And our last one we're going to look at is 37. So in 37, we want to know how many terms to make sure we're within 0.001 of the infinite sum. So when we see a question like that, we want to think one of our errors. So either integral error or alternating series error. Because of that negative, this would be alternating series error. Our alternating series error, we always just do the next term. So we put n plus 1 where the n's are. We don't care about the negative because the an's really saying the absolute value of it. So what we want to know is e over pi to the n plus 1, because that means the next term. We want that to be less than 0.001. Now, if this was something that was nice, we've seen ones where like you multiply things around, get the n by itself and all that. Well, this is kind of messy, so just do it in the calculator. So I've already got in a graphs page, I've got e to the pi raised to the x plus 1. So if you do a control T, we're just going to scroll down until we find what's the first one that's less than 0.001. Keep in mind, we got to be careful of scientific notation. We're starting to get close here. We got 0.0011. Boom, there it is. Notice it switched to e to the negative 4, so that's really 0.3 zeros and then a 9. So n equals 47 is our first time we will be less than that. But we've got to be careful. We got n equals 47. So that means 47 would be on top. We got to notice what we had on bottom. Because we started with 0 on the bottom, and it's asking how many terms, that's really 48 terms. If it had been n equals 1 on the bottom, we would have said 47 terms. If it had said what value of n, okay, then we would just say n is 47. But it said how many terms, so we got to take into account that the 0 is the first term, so 47 would really be the 48th term. Now sometimes we'll have n equals 1 on the bottom, and it would just be 47 then, but just be careful, look and see what that bottom number is. So that's all that we'll do in this video here. The rest of the period you can work on any you would like. On Schoology are posted the worked out solutions for all of the review sheet, so be sure to be looking at that tonight with any that you are stuck on. Test will be next class period. Have a great rest of your day.